We have good to see you all here. Today we have a visitor from the Department of Soil and Water Science and Ecosystem Department. We added an extra word there. So this is Dr. Sam Smith. And if you just look at his profile, I would really say he's a geographer, although he doesn't seem to identify like that. He's an assistant professor in water sciences in the Department of Soil, Water, and Ecosystem Sciences here at UF. He's also the PI of the Land and Water Lab. And his research focuses on couple human and natural systems with applications in sustainable agriculture and land management, water resources management, food and water development, and applied hydrology and hydrogeology. He joined UF in 2018, and his PhD is in environmental geosciences from Michigan State. And he runs, his lab also produces maps for teachers around the state of Florida, maybe in the whole nation, actually. So really, he is kind of a geographer. I can call it closet geographer.
That's right.
Yeah, but take it away.
Yep, thank you very much. Yeah, maybe closet geographer is the right word. I don't even really know what makes a geographer. Right. So I think maybe you could argue it's physical geography is maybe a bin that I would identify with. I have a background in geology is how I started. That's maybe why I've stayed on that side with environmental science, and it just has kind of been growing. I do a lot with GIS, and so maybe that's where the geography crossover exists. I tried to throw in as many maps and GIS things as I could. So I actually run, my lab is mostly a computer-based lab. We're a big data lab, geospatial lab, and so we are very much interacting with what I think you guys would identify with as geography. And so, yep, I appreciate it. One thing I forgot to add just at the end of this, and I don't want to forget, if anyone's interested in sustainability, so Johanna mentioned that my lab works on sustainability. We're pretty critically reviewing sustainability theory. And if that's of interest to you, I'm giving a seminar for the Water Institute next week on Wednesday. I can follow up, and there's an email and a link. I think you have to register, but it's in person in the union, or you can watch it on Zoom. So we won't get into sustainability theory today, but we'll kind of hint at some sustainability things. If you want to extend that conversation, I'll be presenting on that next week. All right, so today talking about Western US irrigation, defined basically as west of the Mississippi River. We'll primarily target on the High Plains region. You can take the same principles, apply them to California and to other places that are heavily irrigated, but we're looking at kind of west of the Mississippi. And what does that mean for the future of US farmland? And in particular, we're really tracking irrigation migration. So that's kind of where we're headed. To start the story, I'm just pulling up a Google Earth image. You can see here, this is obviously a map of mostly the Southeast US. It captures a little bit of the West and a little bit of the northern part. But really what we're seeing is a trend. The starkest takeaway here is the color trend. Right, you see dark green on the right-hand side or in the east, and then you start getting into this brown color in the west. So through on the Gatorhead there, we're down here in Florida. The types of crops that I'll be talking about today are mostly row crops and industrial row crops. So we're talking about corn, cotton, hay, wheat, and soybeans. Those 5 commodities, if you're not aware of it, they account for about, I don't remember the exact number, but I want to say it's at least 85% of all US crop land is just dedicated to those crops. And so when we talk about looking at irrigation and row crops, we're looking at a really large spatial extent. But anyways, wanted to point out this gradient. As we start getting into the High Plains over here, right before you get into the mountain ranges of the Rockies, there's a section of land called the Great Plains region that is heavily agricultural. And you start to question why, right? Because you look at this, it's like, all right, we got a lot of rain, we got a lot of vegetation on the eastern side, but as we start to transition to the semi-arid region, how do we get these little islands of green that show up in this brown? And so you have this sea of brown, sea of semi-arid, yet we have this huge agricultural footprint. I think about 30% of all US crops come from this region. So you zoom in a little bit on this little green island. Can everybody see that? Take a look on the screen if you can't, but we're gonna zoom in there. This is what you see on the landscape. What shape is that? So we can at least be all on the same page. What shape do we see?
Poker chips.
Circles, yeah, poker chips, all right. We see a lot of circles, right? And in fact, it's dominated by circles. If you look at every square inch of this thing, it's plotted out into circles. There's a circle and a square, okay? If you zoom in even further, this is what you see, center pivot irrigation systems. So what is a center pivot irrigation system? You put a well down, that becomes your center point. Then you have this long arm, basically think about it as a sprinkler head, and it rotates or it pivots around that center point. So center pivot. And while it's rotating around, it's spraying water on the land surface and it's watering your crop. So you're giving an artificial precipitation event. And that's allowing us to grow water intensive crops in a semi-arid region. Okay. So starting to look a little bit under the ground, I mentioned that I have a geology background. This is a high plains aquifer. Can anybody say what an aquifer is, just so we're all clear?
Everybody's shy around.
Yes.
An underground water storage.
Perfect. Yep. Let's just call it that. Underground water storage. Okay. It's accessible fresh water in this case. The High Plains Aquifer is the largest U.S. groundwater aquifer, largest U.S. groundwater reserve. I put this title here. It's the largest Western water source. I would highly argue that that's true, but I haven't actually done the stats to confirm it. But anyways, one of the largest in the world, the largest in the US groundwater supply here. So when we think about those wells and those center pivots, what they're doing is they're tapping down into that groundwater reserve and they're pumping up the water from beneath their feet. They're applying it onto the land surface. Okay. We can divide this region up into three different sections. It's one hydrogeologically connected unit. So the groundwater is connected throughout, but hydrologically, surface water is disconnected. We can identify that based on their unique traits. So in the northern part, we have a lot more precipitation. We have well-developed river networks. As you start to make your way into the central high plains, we actually start to get into more clayey soils, less sandy, less permeable soils. And then as you make your way down into the southern high plains, you actually lose all of your rivers. What you end up seeing are what are called playa lakes. They're basically just shallow water, or basins that fill up with water. But anyways, you have really good surface water groundwater connections, really poor surface water groundwater connections. And that's really important when we start to think about pumping water and recharge. When it rains, where does the water go? In the northern high plains, a lot of it will infiltrate and recharge the aquifer. In the southern high plains, a lot of it gets routed to these playa lakes, sits on top of that clay, evaporates away, not a lot of recharge down south. When you look at the land cover, this is just from the cropland database. You see a lot of agriculture. Red in this case is urban. You don't see a lot of red, but you do see a lot of pasture. You see a lot of row crops. And in particular, you see this green footprint, which is irrigated row crops. And if you look at that, that's actually a really large footprint of irrigation. Keep in mind, this is an 8-state region, right? This is just a lot of pumping of the groundwater. So the High Plains Aquifer is a huge resource, but it also is heavily pumped, heavily extracted. Naturally, that leads to groundwater level decline. I mentioned that recharge, especially in the southern high plains, is very little. So as you pump it out and it's not going back in, that means you're going to start losing out on that resource. So if you look at the amount of water, in this case, if you think about the depth to water beneath your feet, how much depth to water have we lost, or how much deeper has it gotten beneath my feet since pre-development? Pre-development in this case is about 1945, we'll say. So since 1945, the central high plains and the southern high plains have lost about 120 feet of water depth beneath their feet. So if you're putting in a well in 1945, you go to X feet, I don't know what it is, let's just say 20 feet. Nowadays, you got to go an extra 120 feet before you actually hit water. That makes sense? Okay, so extreme water loss, especially in the southern high plains and the central high plains. Northern high plains doing pretty good. I mentioned it's really connected with its surface, a lot more recharge, a lot more permeable sediment, able to refill that aquifer. So why do we irrigate in the first place? It may seem intuitive, let's say, but irrigation is a huge incentive for the farmer. In a semi-arid area, if you're growing a water-intensive crop, if you try to grow a water-intensive crop in a semi-arid area without artificial applications of water, it's not going to do very well. You still will get some production, but it won't be that much. In this case, if you are to irrigate, you can get anywhere between 2 and 4 times the amount of production. All right, so you're doubling up to quadrupling what you would have produced had you just produced dry land. All right, so the economic incentive is really high. Naturally, when there's so much irrigation going on, I mentioned that it leads to water loss. We can track that water loss. We've switched it now from depth beneath your feet to the amount of water that's left in the pool. All right, so how much water is left? The Northern High Plains is actually doing really stable. They irrigate a ton, but a lot of it goes right back. Not that big of a deal. Central High Plains and Southern High Plains, though, are losing water, and they're losing water quickly. Southern High Plains, especially, has lost half of its known water volume since pre-development. So when you start to think about sustainability, sustainability always has to have a time frame. What is the time frame in which this action can endure through, continue until? Right? The Southern High Plains, in some places, is looking at less than 10 years. In other places, it's more. Central High Plains, you're looking at minimum 25 years more. So Northern High Plains, pretty solid. This is where it starts to get interesting, and this is where we start to connect into other things like technology. So this is a cross section. You can see the black line in the Southern High Plains. This is the amount of water that's left in the pool. That's saturated thickness on the y-axis, and on the x-axis is just the distance along that black line, just a cross section. So going back to pre-development 1950, this would be the amount of water that's in the pool. Go down to 1970, you've lost water. 1990, lost water. 2000, lost water. You can see that we're losing water. And in some cases, we've already exhausted the water. Right? This only goes to 2012. Here we are in 2022. Irrigation hasn't changed. So we can envision this, right? We should probably update this figure, but it can keep on going. Some places are going to be completely exhausted. So just, again, so we're all clear, what happens if you exhaust irrigation in these regions?
Revert to dryland farming or migrate away.
Yep, migrate away, revert to dryland farming, change your crop practices, retire. There's a lot of things, right? But basically it's stopping business as usual. And historically, I mean, there's a whole culture that's set up on this center pivot and pumping, like the attitude of pumping. If you've ever been in that area, is anyone from this area? Yeah, is that the prevailing attitude?
Oh, yeah.
Yeah.
I grew up in liberal Kansas, southwestern Kansas.
Yeah, very cool.
Right in the middle of your state.
Yeah.
Right in the middle of that red dot.
Yep, perfect. So it very much is embedded in the culture, right? And there's a whole different conversation to have about like who's responsible for that and all of that kind of thing. But anyways, what I want to point out though is this red line. You can see this red line that says 9 meters. This is a really important line, right? When we talk about running out of water, people think about that as like, oh, there's no water left. That's not the case. If you live in this region, there's going to be enough water for you to live and drink and do that kind of thing. But what it means is that we can no longer pump in the same way at the industrial level as what we were doing before. So once you fall below 9 meters, it becomes too prohibitively expensive to try to extract the water. Does that make sense? Okay, so below 9 meters, that's the mark. Like we're really trying to protect this 9 meters. We're really trying to slow it down so we don't hit 9 meters. So how do you do that? What's like probably the one thing that comes to your mind? How do you slow down water loss other than like using less? If you fix the idea that income, like we don't want to negatively impact income, how do you slow down water loss? Oh yeah, they actually call that aquifer storage and recovery. We won't get into that today, but that is one option here.
Change from sprinklers to drip.
There you go. Change your irrigation type, the different types of irrigation. So in Florida, there's not a lot of center pivot, but what you do see are a lot of drip lines, right? What are drip lines? They're those little plastic tubes that go right along the ground. They just leak out water and they do a really good job. They're highly efficient. Like 95 to 100% of the water that's applied goes straight to the commodity. But when you think about industrial agriculture, if you go back to that cover photo, the huge tractor and the combine, that would rip up drip lines like none other. And we're talking about a very large spatial footprint. So drip lines are just not cost effective when we talk about, industrial scale corn farming. But we can take those principles and apply them here. And so what we've done is we've upgraded technology. Historically, we do this flood irrigation. This is primitive. This is ancient. This is about 50% efficient when we talk about water that goes to the crop. It's actually more efficient than that because some of it will go back to the aquifer. It's not entirely like half is lost to the atmosphere. Center pivot though is a little bit different. Center pivot is what we just talked about, where you apply it over the landscape surface, but as you can imagine, like watering your garden on a windy day, you lose it to wind drift, it lands on the leaves, it evaporates away, it doesn't all go to the root zone. So what they've done is they've added what's called LIPA, low energy precision applicators. And what it is, it's basically just you can call it a retrofit or something to a center pivot. It takes the center pivot, instead of an overhead spray, it now runs it through basically a drip line that drags along the land surface and applies water right at the root zone. And this efficiency is up at 90–95%. So we know that we're becoming more efficient in our technology. And then if we look at the adoption of that, pulling Kansas as an example, you can see that LIPA really exploded in 1996. It is now the dominant technology across this region. These data are really only known for Kansas or reported for Kansas, but you can see it show up throughout the high points. So in this entire region, we have become more efficient. Right? Question here is what happens in 1996? Anyone want to take a stab at that one? Why is there such a huge spike in 1996? What's that? That's exactly right. Farm Bill. So in 1996, the Farm Bill comes out. They have an EQIP program. It's Environmental Quality Incentives Program. Government basically subsidizes the adoption of efficient irrigation with the hopes that it slows down water. Interestingly, in a whole another side conversation, this is like the #1 way that policymakers try to adopt efficient practices or slow down water loss. When I applied for my job in Florida, there was a headline, that was in 2018, Veneer, this is year 5. In 2018, the St. John's Water District, which is Gainesville, put out $1 million so people could switch to efficient systems. So it's something that it's still very prevalent. Do we think this is a good idea? Bad idea?
I'm thinking it's a good idea.
Yeah.
The option is more expensive.
Okay. All right.
But that's just from the perspective of someone who's been working in the energy section.
Yep.
So that tries to limit people's energy use.
Yes.
Building a new power plant, it's a lot more expensive
Mhm.
than to give incentives for people.
Yes. Okay. We're all saying yes. This is exactly right. But let's look how this plays out in irrigation. All right. So take a look. This is revisiting that percent volume or the amount of water that's left in the pool. If you look at 1996 and beyond, we don't really see any change in water loss. We know that we have become increasingly more efficient and radically more efficient, but it has not reflected in water loss. Any idea why?
More efficient, we added more.
Yes. So this goes back all the way to 1866. I'll introduce it in the next slide. But what we saw is that farmers actually irrigated more. They increased their irrigation in this region by about 10% over just a 5-year period. Why? Because it's cheaper to irrigate. So now that it's cheaper to irrigate, they can irrigate more area for the same cost as what they were doing before. And you actually see this in lots of other things too. Like the one thing that I think is hilarious right now, it's Volvo has a commercial and it's about electric vehicles. And it just cracks me up because the slogan is like, do more. It's like, drive more miles, do more. It's like, yes, thanks. This is exactly what I'm talking about, right? This is called Jevons paradox, this principle that efficiency leads to more use. This is going back all the way to 1866. And it's funny that it hasn't actually made its way through mainstream, just like understanding. So I always try to put this slide in here because I think it's important. As the cost of use goes down, or as the efficiency goes up, total use goes up, all right? With efficient systems, cost of use per area goes down, which means we can now irrigate more for the same cost as what we were doing before, especially when the government subsidizes the investment. The big cost to efficient irrigation systems is the upfront cost of getting the system into place. The government pays that off. Now you're only dealing with operation costs. Operation costs drop. You can irrigate more area. This actually was figured out in coal and oil, I mentioned back in 1866. So there is an extra interesting research question, if anyone wants to pursue it, of how this plays out in renewable systems, since all of this is stemming from non-renewable systems. But as far as I can tell, it's holding true in renewable systems too. So let's take a look. Wichita County, Kansas, 1984. What shape do we see on the land surface? Squares and rectangles. What does that mean for agriculture? It's not center pivots. Yep. This is indicative of dry land irrigation. Fast forward to 2015, and we can see that that's changed the center pivots, right? Not entirely, maybe about half, right? But we see adoption of irrigation. There's expansion of irrigation. So the question that I'm interested in is, what does this actually mean for the country? This is a really poor image. Don't look at this and critique it in terms of the map. I didn't make it, and I can't remake it, and so I still use it. But what this is looking at is the change in vegetation between 2017 and 1985. Right? And what you'll see is a greening effect. So it's becoming more vegetated. Where is it becoming more vegetated? It's becoming more vegetated in the Corn Belt. It's becoming more vegetated in our heartland of agriculture. Okay. So question is, well, why is that the case? Maybe we're becoming more irrigated. Maybe we're seeing that yield boost from irrigation. And so it would be easy to figure out that answer if we had those data, right? So if you look into the agricultural record, USDA does a great job of collecting data. They've actually gone back as far as 1866, and they have state reported average yields and total area. So if you want to know what did Kansas produce in corn in 1867, that data or those data exist. It'll tell you the yield, it'll tell you the total area. But it doesn't make the distinction between whether that corn was produced with irrigation or dry land, right? And in Kansas, where we know there's a mix, that's really important. In other places like Illinois, we know that it's predominantly dry land. It's not that big of a deal. But we're trying to figure out, is the US becoming more green because of irrigation? Those data just don't exist. So, like I mentioned, this is what you would see. You'd have the year, you'd have the reported yield, and you'd have the reported area. And that's the extent of it. So you can't actually answer the question, is this due to irrigation? Because those records are non-existent. So the follow-up question here is, can we actually parse out an irrigated signal from these records? If there is that yield boost, we should expect to see that be reflected in the record. So how can we actually go about getting it? And does that record exist? Just conceptually, what you can do is start by grouping all the dryland states. So states that you know are predominantly dryland. In Iowa, they're not irrigating historically. In Illinois, same thing, right? So if you look at a reported Illinois yield, it's going to be dryland produced. If you look at California and they're growing corn, they're doing so under irrigation practices. So you can group the dryland states and you can group the irrigated states, and you can map those plot those out. So on the x-axis here, we have time. On the y-axis, you have yield. So through time, we can see how yields have gone in those dryland states. Call this the hockey stick effect, casually. I don't know if anyone's coined that, but this is basically the birth of modern agriculture. Like post-World War II, fertilizers, new practices, everything take off. So we're getting really good dryland yields. You map out or plot out those irrigated states, and you see a really similar shape. But what's interesting is you actually start to see irrigated states outpace dryland states. And if we look at corn, it's like there's no reason why California should be outpacing Illinois or Iowa in corn production, right? Just doesn't have enough water. So naturally it's from irrigation. So we can call the difference between those two that irrigation enhancement. It's the boost from irrigation. All right. And so there is a signal that exists in the record. We just got to go get it now. So how do we do that? And I've spent about 5 years trying to resolve it. And putting out what I'm calling the parsed agricultural data model. It's operating at the county level, not the state level. I've capped it at 1945 through current, but it can go back as far as the data records go. Like I mentioned, it's for those main commodities: corn, cotton, hay, soybeans, and wheat. I think I can also do it for other commodities too. But then, and also there's a whole bunch of agricultural census and survey data that the USDA provides that I can feed into it. Collectively, it's about 12,000 individual scripts across 3 different languages. It's pushing at this point now. I need to update these numbers. About 1 million lines of code. It's across 3 different languages, and it takes about 4 days to run. But it's done, and it's working, and it's looking beautiful. I haven't published it yet, so enjoy these results. So to start, what you need to do is, like I mentioned, group those things, those end members, the dry land and the irrigated states. You can substitute that with counties too. But really where we're going to start seeing these changes, or those initial changes, are going to be in those mixed states like Kansas, where they do have some access to irrigation, do have pre-existing irrigation practices. We want to see how that changes through time. we need to start figuring out what are the dynamics that lead to crop production in those regions. Take what's going on in dry land, take what's going on in irrigated, take what's going on in mixed, and we need to organize those, right? What precipitation did Wichita County, Kansas get in the 1986? What soil type did it have? What was the average temperature? What was its growing season like? And we need to accumulate all of those things. And we actually do have those data, which is really cool. We have a really good data record for lots of stuff going back to at least 1945. So once those are in place, what I used was a machine learning technique called boosted regression trees. This is just a simplified version, but what it will do is it'll take a variable. In this case, it'll just take a soil type. What soil type are you? Are you a mollisol, yes or no? So are you silty, yes or no? If you're no, what was your recharge like? And it basically just ping pongs through these decision-making factors. And then ultimately will make a guess on the predictor variable, or sorry, the independent variable, which is, the dependent variable, which is the yield. And so it's estimating yield at that point. And then what it will do is it'll optimize itself to where the residual is small and it's making good guesses. The other thing that it'll do is it'll give you the influence of each variable. So this is another summarized figure. So on the y-axis are all just random variables that are thrown into the model. On the x-axis is its influence type. So this is a summarized version of the influence of 2017 for corn. So how do you predict corn? Well, you can say if soybean did really well in that year, corn also did well in that year. You can also start looking into the geography. So where is this corn being planted? What's its elevation like? What's its solar radiance like? You can start looking into the hydrology. When did it get its water and how much water did it get? Interestingly, soil is not a strong predictor. Any idea why that would be the case?
If I had to make a guess, I feel like soil data, like at a smaller scale, can be very variable, because there's not data sets available to account for that.
Has anyone used like Sergo data sets? Are they high resolution or low resolution? I think those are one of the most annoying data sets to work with. They're just so bulky, just because we do have really good data resolution, even down to small footprints. So it's not that factor. What it is soil diversification. We've optimized which soil grows the best corn, and we only plant that. And so there's not enough diversity in corn. So soil is not a good predictor, just because there's not a lot of variability.
Fertilizer use too.
Yes, so that's a whole different dimension. And unfortunately, let's follow up with that after. But what happens in this model is it actually groups everything into like a time variable. And then that's one of the places where I'd like to go next in my research, is now applying this at the field site where you actually have, what are the fertilizer practices, pesticide use, all that kind of stuff. We don't have data for those at the county level, or even at the state national level. Okay, so once you have identified what's going on in irrigated states and then going on in dryland states, you could say, based on the conditions in dryland states, if a mixed state were to grow corn under dryland practices under their conditions, now we can estimate what dryland yields would have been. Same thing for irrigated. So what this model will do is it will start with the reported the reported values, and say, here's your area, here's the reported area. Here was the reported area that produced corn. Here was the average yield of corn across that area. Right, so that's what's known. Then what the model will do is it'll estimate. It'll say, okay, based on the conditions in which you were growing, if you were to use irrigation, this would have been your likely yield. If you were to only produce dry land, this would have been your likely yield. And once you have yield in place, you can actually backtrack and start to parse out areas as well. So we now have a data set that can estimate irrigated yields, dryland yields, irrigated areas, dryland areas. Going back to that original question of what does this look like for the US, now the data are in place and we can track migration and other dynamics as well. So what are some of those dynamics? I'm interested in irrigation metrics. And so defined a few here, irrigation dominance being one of those. So in this case, what is your percent irrigation? Going back to that Kansas figure, and we said it kind of looked half and half. I pulled the same county, and so it was 47% irrigated, and it matches visually with what we were looking at, roughly half. Right. The other thing to look at though is what I'm calling irrigation dependence, and this is the inflation, or you can think about this as production risk. It's if I were to lose access to irrigation, how much yield would I actually lose, or how much production would I lose? And so in this case, Wichita County would lose 22% of its production if it had to switch to only dry land. Does that make sense? And then naturally, the next thing you can do is connect that to revenue. So how much money would they lose had they only switched to dry land, or if they run out of water? Or you can flip it positively and say, how much money are we getting from irrigation? In this case, just that county in that year got about $7 million. That doesn't include operation costs, so I don't really know what that would look like. But the idea is it's not a small number. It's not extremely huge in agriculture, but it's not insignificant either. And this is only just for one county. You can imagine this would be the case for a lot of counties. Okay, so the cool thing is that you can now look at this at the crop level too. So across the country for corn, for example, how much of our corn is irrigated? And that's the irrigation dominance metric. Roughly 40% of all US corn is irrigated. Soybeans is a little bit more dynamic. You don't see this steady increase and then the plateau. You see an early spike, then it kind of goes to nothing, and then it comes back. We'll talk about that in a second. Hay was really popular back in the day. It's kind of like phasing out. Wheat has just been kind of this like old reliable, right? About 20% consistently through time. Are you following this? Any questions at this point? What time does seminar go till?
5.
Oh, okay. Okay, we're doing great. Is that for a little after 4:30?
Mhm.
Cool.
The clock's been fixed.
Excellent. Okay, so this is going back to that dominance, but what I did is I zoomed in on the black line. Or sorry, I said wheat being old reliable. I actually took it off. But anyways, black in this case is total. Sorry, I got ahead of myself. Total is now zoomed in, right? Those other lines have been removed. And if you notice, I've scrunched it a little bit to really amplify the signal, the up and down signal. Okay, so on the y-axis, we have that irrigation dominance. On the x-axis, we have time. You'll notice that we have this really early peak in irrigation. It starts to fizzle out and then kicks back up. Why do you think it kicks back up? Pretty sharply. Close. Yep. U.S. Biofuel Mandate comes out in 2005. All right. What's the Biofuel Mandate? Does anybody know this? Specifically through biofuels, right? What are good commodities for biofuels? And what else? Corn and soybeans. Yep. And so we start to see the heavy irrigation of corn and soybeans because of the heavy incentivizing of boosted corn and soybean yields. Just to go back, that's what's going on here with this soybean. Notice here the really sharp uptick around 2005. Okay. You can also, like I mentioned, connect this to dollars. Just advice. If you're ever doing research and you want to have real world impact, just connect it to dollars. It's like the easiest thing to do. And it's the easiest way to like cross disciplines and make things matter for people. So anyways, if we're looking at revenue from irrigation, that irrigation enhancement, right? Notice that the y-axis is in billions. And so this is through time, annual. This is how much money we're getting from irrigation at the county or at the country level. Soybeans, corn, hay. But what's interesting is this total. Right? And if you're looking at this as a data scientist, there's a couple things that stand out. And typically it's going to be those highs and lows. Right? And in particular, we're going to analyze these highs. What do we think leads to really high returns on irrigation? Droughts. Yep. Anything else? Drought was the one that we haven't talked about yet. The other one we have. I slid it in there subtly. Market prices. Right? When market prices are high, there's an incentive to have higher yields. And so if corn prices are extremely high, then you're going to see people irrigating corn. Right? They're going to grow corn. They might even switch from hay to corn. Right? You're going to see an increase in that commodity. The other thing is going to be drought. Drought leads to actually really high irrigation incentive, revenue, even if yields dip. Because in these places that are semi-arid, if you have a drought, you might not even get a return on anything. You might not even get yield at all, right? So even if you get a little bit of something, that's better than nothing. In other cases, maybe you can even maximize it. Like you really optimize the weather. You have really great warm growing conditions, a lot of sun, and let's crank this thing with water and fertilizer and get it going. Right. So there's interesting dynamics there. I mentioned connecting this to the real world. The one question that I think people would ask when you actually start talking about farmers and growing conditions, it's, okay, well, how much would I actually make? Or how much more yield could I get? How much more money could I get if I'm a farmer and I'm considering adopting new irrigation? Right? I look at this map and I see, okay, there's a lot of incentive for me to do it. What is that incentive? So let's say you're a farmer in Illinois and you're looking at corn. If I were growing dryland conditions, this would be my yield, somewhere in the 175 to 200. If I were to irrigate, maybe I could even push 220, 225, 250. Right? And you look at that and you're like, oh, well, that's a huge increase, right? Well, compared to the high plains, they're getting 2 to 4 times, right? So like 400%. So 25% increase is not nearly as much as like 400% increase. So this is that irrigation enhancement percent. So what's the percent difference between the two? So in Illinois, if you're a farmer, you could be looking at, say, 25, 30% boost on your yield. Right? I mentioned that those revenue costs don't factor in operation costs. And if the government's not subsidizing those, irrigation is just a huge cost, right? And so that margin of 25% might not actually be worth it. Does that make sense? Okay, but as that cost goes down, that margin becomes more and more enticing. Does that make sense? Okay. The second thing is, well, what does that look like for other commodities? Because in like the dryland Midwest, they do crop rotations. They're not always growing corn. Every once in a while, they'll throw some soybeans in there. Some people will go back and forth seasonally. But anyways, now we have the data in place to be able to consult and answer those questions. Okay, so this is looking at the national level. And these are actually, like I mentioned, this hasn't been published yet. So this is, I think, the first time I've actually showing this figure to a public audience, which is, I think, is fun. So this is for 2017 irrigation enhancement. There's a couple of things I want to point out. First is the high plains. I mentioned that they're getting like 2 to 4 times. And if you go back to that early graph that we showed, right, they're well above 100%. They're actually like 200 to 400%. So naturally they would be irrigating. But then you start to look over here into the eastern part and we're down into like 1 to 50% range. So what's the threshold at which somebody starts to think this might actually be worth it for me? Okay. You'll notice that there's some blank spots in the Corn Belt. In those places, it would have actually been a negative impact to irrigate. They had sufficient water, if not too much water already. You can't just keep adding water because eventually your yield's going to decline. Okay, so that's kind of where we're at, is like, it's not going to be this massive boost, and it's not even going to be guaranteed boost. So in what scenario would a farmer start thinking, you know what, maybe that 50% makes a lot of sense for me? Imagine you're a farmer. You hear it all the time in your college classes. That this is really important. This is the future of our world.
Do you perceive there's going to be a lot of volatility in rainfall?
Yep. Due to what?
Climate change.
Perfect. All right. So start thinking about climate variability or volatility in the market. Okay. There's going to be scenarios, if you're a farmer and you're hearing like, hey, the Midwest, guys, heads up, it's going to be drier, it's going to be hotter, you're going to have these more flood events, all these things, right? It's not that the flood events are important to you, it's that the drought events are important to you, okay? And so maybe that 50%, even though it might not be something I do consistently, in the event of a drought year, that might not actually be the difference between making it or breaking it. And that can actually be a really important decision-making factor. So stay tuned for some future work, but one of the things I'm looking at is how farmers have historically used irrigation to cope with drought and what does that mean for the future. So this is conceptually the story of what is happening. You've seen this is Jevons paradox. On the y-axis, you have cost, on the x-axis, you have total use. As cost goes down, total use goes up. So as we become more efficient, total use goes up. What that leads then to is this migration. As the cost of use goes down, farmers then might actually start to adopt new practices. In places in Kansas, for example, where it's not 25% enhancement like Illinois, it might be 150%. Right? Before it was like, well, I don't know if I really need this. Well, that 150 is now actually quite affordable, let's say. Okay. And so we can start to track this migration, and we know that it's happening. And then ultimately it comes down to a decision-making factor. So you can call this the 3 ABCs or the 3 M's or whatever you want, but eventually you start to get new adoption once it becomes favorable in terms of your operation costs or your revenue relative to your irrigation enhancement. What boost am I going to get? What protection from climate variability am I going to have? Is it worth my investment? So this is what we've seen. This is from 1977 to 2017. This is the percent change. So if you're red, you are adding irrigation. If you're gray, you have lost irrigation, or you're not growing corn, or you had no change. So where are we seeing migration show up? And this is what it looks like. Does anyone think this is really cool? Because I do. I was hoping there'd be a lot more colors, you know, and like stark things, but there's a lot of data analyzing this. So this is going to be cool stuff coming out soon. But anyways, this is the trend, right? We're seeing an eastward trend. We're seeing not a west. We're fully allocated in the west. Right? Let's move to the east, and there's new frontiers, let's say, for irrigation. And so you can pretty well draw a line and say irrigation is moving east in the US. So what does the future of agriculture look like in the US? Especially relative to irrigated row crops, you're going to start seeing new attitudes, perceptions, mentalities moving east, right? It has not been unheard of for farmers in Kansas to say, that's it, I'm done, I'm moving to Georgia, right? And I'm going to start corn farming in Georgia. And I'm going to take those same practices and I'm going to bring them over, right? So there is a proximity effect, and there's also this like random effect that we're still trying to work through. So that'll happen too. I'm almost wondering too if there's waves. Right? Like we can go back. I didn't track this annually, but we can develop a movie and like watch it happen. So do we see actual movement from some sort of central proximity, or is it random popping up? But I'm expecting there to be some sort of wave effect as well as this thing kind of moves. We'll see. Maybe 2 weeks away from having results on that. But eventually what it comes down to is, what are the conditions in which you're growing? So this is just the Midwest, for example. Here, this is clipped that irrigation enhancement. Here's the clipped adoption, or places that are adding irrigation. Eventually, what it comes down to is, what are the factors in which you're growing? What is the climate like? What are the soils like? What are the other commodities? Are they doing well? Or are they not? In which case, it's not that other commodities lead or are driving factors to the growth of a commodity, but it is generating an agricultural market. There's places in position, blanking on the word, like grain storage. Yes, and elevators is what I was thinking. I don't know why I'm blanking on that. Anyways, the infrastructure is in place for an agricultural market, and so naturally you'd be more incentivized to take on different practices in those areas. Following that up, obviously with some bigger picture research questions, like does the Midwest or Georgia or the Southeast or the Northeast, do they actually have the capacity or the suitability to take on new irrigation? What does that look like for groundwater management? What does that look like for, environmental risk? Is it actually worth it? We do see that it's showing up. So some people think that it can be done, and they are doing it. So now we can actually start connecting this to management as well. Maybe we can get a little bit proactive in our approaches. If we know that this wave is coming and we can potentially track when it'll even arrive, now we need to start thinking about, what does it look like to manage this incoming flux of irrigation into these regions? Okay, so some general takeaways. The first is that efficient technologies can intensify water use. We've hit this one pretty hard. This is something that we see in agriculture. It just is a principle that exists that I think people need to be aware of. The second is that efficient technologies can be adopted in places outside of their intended use. And I say that because if you go back to that sequence of photos, and we're talking about high plains water loss, LIPA was developed for places that are running out of water. It was developed for the Great Plains. It was developed for California. It was developed for water scarce regions, right? But once it's on the market, it's on the market, and it's now available to other people. And so we're starting to see it show up in places where it was never really designed to show up. Right? Not that that's a bad thing, just that it's a relationship between what's available to a farmer and how they make their decisions. The third is that it is becoming more profitable in the eastern US, especially once you add climate variability or risk in those other things. As agricultural markets become more risky, irrigation becomes more of a protection or an insurance, okay? And as irrigation costs goes down because we're becoming more efficient in our practices, especially as we're hitting it from both sides. We're hitting it from the irrigation technology. We're also hitting it from the cultivars that are the different seed types. We're building out drought-resistant commodities and all these things. So it's coming from both sides, and it's getting more and more reasonable or rational or economically favorable to adopt these new practices. Fourth, that naturally leads to an interesting water management question, and that is a fruitful research pursuit, in my opinion. I think there's going to be a big field moving forward in what does it look like to manage agricultural water use in the eastern US. It's something that, in my opinion, has kind of gone under the radar for quite some time in terms of total quantity. One of the things that's you hear a lot as a water scientist is the eastern US is water quality and the western US is water quantity, which is very, very much true. But I think there's this like growing quantity wave that's going to be hitting the eastern US. Who knows how long into the future. The other thing though is I think it's important to point out that it's really easy to take these things as like doom and gloom and risk is bad and all of this stuff and new adoption of irrigation is bad and that'll lead to these new things. I don't necessarily think that's the story to be told. What I think is that what it does is it helps to optimize our agricultural landscape. The earth is dynamic, it's always changing. Agriculture should not be any different than that. Agriculture has had a very static footprint for a long time. And I think what we're doing is we're hitting a point where that needs to evolve a bit. So it would make perfect sense for the Great Plains to basically say, why are we growing corn here at all, right? Why don't we become smarter in our decision-making, become more resilient in how we have our farming systems? Let's just kind of avoid this water stress situation and do something different, right? The trade-off is that that demand for the product doesn't change. Somebody has to pick that up somewhere. Maybe it goes to a different country, or maybe it goes to the eastern US. Okay, and so I think that there's opportunity for the eastern US to potentially offset some of the environmental challenges that are currently, that we're holding like responsible on the western US. So anyways, that's just an opinion you can take away. Okay, that's all that I had. Happy to answer questions.
I've got so many questions. Yeah, I thought you got the best one to ask, and that's it. Don't say anything about energy costs.
Yes.
Issue. One of the reasons that the central high plains aquifer is so irrigated is because we give them the natural gas field below, and the oil companies would come out, drill wells, and just basically give the farmers free fuel for their pumps. But what happens with the rest? You know, as energy prices go up, are going up, you know, how is that going to affect the migration of irrigation?
That is a really good question. I'm currently writing a proposal to be submitted to USDA in a week about this question. Yep. There's a group out of Michigan State that does a lot of energy costs, like factor analysis, and then we're working with a group out of Dartmouth too. And so this question, I mentioned only the environmental side, but the energy is the other one. That is the driving factor for these operation costs. It's like it costs a lot of money to pump water out of the ground. And so what does that actually look like, especially energy security, going into the future, cost and all that stuff. So we're working on it. I don't have any input into that.
Particularly as the aquifer is more and more depleted.
Yep.
It's
Yep.
much harder.
That's right. Take a look.
So I have a whole bunch as well. Given you showed my study area from my PhD, where I study climate change impacts on agriculture. So in terms of your model, you talk about what's known in terms of acreage and crop. What kind of validation did you do with that data set that you based your model on?
Yeah.
Because a lot of that data is not great.
I don't.
I'm being nice.
Yep.
It's public.
It's true.
National data.
Don't think I have the figure in here. So doing a lot of, if you get into the USDA data set, there's the survey, there's the census, they have this farm and ranch survey. The High Plains actually has really good nodes of collected irrigated data. They've actually have set the precedence for collecting irrigated data. So there are a few places that exist where we do have these known points. I don't have it up here. So for the validation calibration stuff, that was all just data splitting and working through it and looking at predicting itself on the variables that it's using and all that kind of stuff. And on the county level, we're doing really good. We got R squareds in like 0.96 for corn.
But are you talking about in terms of your model versus what they reported?
And so then that's the follow-up, is how does that actually compare to what's being reported? And if you look, they're plotting on the same lines. So we're plotting relative to what is known through the surveys, which is different than what's in the census. And so what you're identifying is that there's a lot of inaccuracies in the census, and we can actually uncover that too with our data. And when you look at it, you can see, well, like, this is a mess and this is missing and all these things. Yeah, it's agricultural data is an interesting piece to work with.
So I can't rely on the national crop data layer.
There's a lot of people who are working on those things. Like, let's take remote imagery and let's calibrate. And the irrigation figure that I showed with the green, I think there was a paper that came out not too long ago that was saying that was 80% accurate or something like that. So it's not terrible, but it's also not like spot on.
So in terms of the Midwest, when you showed the map, looking at kind of the question of at what point will people change at a more local level, I think so I studied farmers in that region for my PhD. And so we actually did a lot of interview data with a lot of the farmers. We were looking at the 95th percentile large farmers who had resources and were able to change and adjust practices. Number one, they all told us climate change doesn't matter. It was a climate change study, so it was always nice to hear. But their argument is, we're just going to breed in new cultivars, and we already have, and we can breed in whatever we want. But the second thing was a lot of it was social and resources based. So who and what individual farmers were able to adopt irrigation or any other practice was a function of a lot of social information about those farmers, their education background, as well as financial ability. And I wonder, because you have that nice map where, you get down at the county level and the percentages. And I wonder if you've done anything with that in terms of, rather than just at what number would people change, but under what situations will different people adopt different types of practices. Might be really interesting.
Yeah, that would be really interesting. I don't have that. So in terms of where I'm at in my program, my lab is currently working on like lots of different directions. So this has been just carried like on my own time. This is the one thing that hasn't had a deadline. So it's one thing that gets pushed back. So I've been trying to get this thing out since like 2019 and here we are in 2022. And so anyways, where I'm at right now is like, this is it. And so pretty soon we'll have the final stuff within like probably a week or two. And then what should happen would be a natural follow-up is to take the social factors into consideration, especially compared to the map that actually shows the change, this one, right? And see, okay, well, these are the places that have adopted, why, and are there any relationships between?
Do you have data change on that? Because I know you have it just color-coded as one, but you mentioned a wave. Do you know
I can't, I haven't done it yet.
That would be interesting.
Yep, I can do this at the annual level from 1945 to 2028. I just put this together not too long ago just to see what, if anything, actually showed up, if I'm onto something or not.
And one last, and then I promise someone else can ask. I never ask questions, so they will probably done. You should look into the GRACE satellite if you haven't, because then it will give you the actual water use for the time period that it's been measuring at least, and that would be a great calibration. And also really get at that issue of that variation across your aquifer and storage and use. But that's really fascinating when you get into that too.
Yeah, this, my opinion is that I got hired on Florida for this project. It's like, this is what I went in with my job talk, and other things have kind of trickled in, but there's so much to uncover from this. And so I know the people to talk to in those situations. I just
Good fun.
If you're interested, I'm always open to collaborating. I think I saw this one.
So this is more of a comment than a question. Just, I'm trying to be politically neutral with it, and it's not. Given that the Farm Bill and the subsidies
The electorate, okay.
Do you feel like there's gonna be pushback if they're seen instead of climate change buffering strategies?
Who doesn't think of climate change? Come on, see.
Well, yeah, but that's what I'm saying. Is
Yeah.
something where people can do climate resilience,
So
and that becomes a major strategy for using something that's the subsidy directive that big less.
yeah,
But it's fine, because some use the phrase climate variability, which for the Midwest covers all ill.
that's right. I don't know that answer. I know that there is a lot of without getting too much into it, like this is an interesting topic in rural America. I don't know what that looks like in terms of the trajectory. I'm hopeful that future farmers are at least more acclimated to the terms and aren't as turned off to the terms and, you know, in some cases would be more open to those things. I don't know what that actually looks like. So that's a good question. I don't have an answer. I'd have to defer to social scientists and their best guess.
Maybe in 3 years we'll find out
Yeah,
what
that's
the
right.
exact
Yeah.
are for using the subsidies.
Yeah, I mean, I grew up in the Midwest. I remember some pretty big droughts that went through, you know, and I think if rather than talk about it in terms of climate variability or climate change, if it's just like, hey, this thing lets you cash out in a drought year, you know, like I don't see any reason why farmers in my circles would look at that as like a, you know, what is this witchcraft, you know? Yeah.
Okay.
And I personally, I have a soft spot for farmers too. Like I grew up in a farming community, and I like to give farmers credit in how they approach things. I think they're, you know, innovative, and I don't think that they're as closed-minded as the perception is given to them. But I'm also not a social scientist, and I haven't actually measured them. I'm only talking about the people that I personally know.
Right, I mean, things like the Farm Bill are so political.
Right.
That,
What was really cool was I was at Michigan State in 2016, I think is when the Farm Bill, it's every 4 years, maybe it's 2018, I don't remember, might have been 2018. But Obama, no, that's not right. It would have been, yeah, what, I'm lost track on COVID messes up timeline. Anyways, Obama signed Farm Bill at Michigan State when I was at Michigan State. And it was just like really cool to see that dynamic come together, especially with rural Michigan as being like the hub for it. And Michigan obviously has its own swing state ability, enough that there's a large rural conservative footprint that would still have like supported the situation. So anyways, yes.
Has the production offset potential of the east as the same migrates perhaps east been diminished somewhat by erosion of urban areas, rural areas of farmland and also I think about Florida, I think about citrus industry, you know, and I think the 30s where it was built. Well, even when before that, I used to go through and drive, and it was citrus farming, and now it's basically, you know, the villages. Is this happening elsewhere in the east where the actual, you know, offset potential is diminished because of these?
So I actually put out a paper, and I had the slides in here this morning, and I took them out because I was like, no one will act. That's not even related. But in 2016, I believe, I built what's called the land transformation model. So you can, I used it, I didn't build it. Brad Pichinowski did that for you. But you can simulate what future urban areas are going to look like. And so I did that specifically to answer this question of what does it look like for urban area consumption of fertile farmlands. And so we ran it in two scenarios. We ran it unprotected, and then we basically gave a score or a fertility value to the soil, then ran it again and said, you can't develop here. Now, what does it look like? And so the conclusions from that is that urban footprint in the grand scheme of things is relatively small when you think about like how big the US is. But it was strong enough that if you put in that protection of we're going to protect our most fertile farmland, what it ended up resulting in was urban densification. And so at the time, I was like, hey, that's a good idea. Post-COVID, like densification maybe is being reevaluated. I'm not sure. But anyways, it's not a large footprint, but it's not insignificant. It's something to think about. Because typically when you think about development, we are developing the easiest to access and most suitably located. We're not actually given a value to the fertility since the value of real estate is significantly higher than the value of farmland.
So lots of great questions. It's actually 5 o'clock, so this class is officially over. I think we give Sam another round of applause.